lectures on bosons, and then you will have tutorial on Friday, and then we can continue, because this is the middle of the course, then we continue with the lectures and one another. So for bosons, we are going to discuss ideal and non-ideal gas. This is what we start to do today. We end with Gross-Pitayevsky equation, and we find fixation in Bose-gas using Gross-Pitayevsky equation. On Wednesday, we discuss the spectrum of interacting Bose-gas using Bose-Einstein transformation, and we discuss lifetime of quasi particles. Next Monday, we discuss superfluidity, and then on next Wednesday, I'll give a summary with transparencies, with slides and optical traps, magnetic optical traps. And also, if time permits, I show you some slides about real Fermi surface of metals in order to conclude with Fermi. And then, as I said, next Friday you will have a tutorial, and the second part will be more strongly correlated. In a sense, we will have 4 lectures on superconductivity and 4 lectures of magnetism of strong conductivity. So today we will have lecture number 5. So Bose-gas. So let's start with ideal Bose-gas. Bose-Einstein condensation. So what we said in the first lecture, we begin with non-interacting system, that the wave function of n identical non-interacting bosons, psi bosonic, which depends on psi1, psi2, is given by symmetric combination. You can have certain number of particles, n1, n2, in the states 1, 2, and so on and so forth. You have a proper normalization factor, and you have a sum of all permutation P1 psi1, phi1 psi n. So this is how the symmetric, fully symmetrized wave function looks like. And we said that the occupation number for given state characterized by the wave vector k can be 0, 1, 2, any. There is no Pauli principle because, as I said, the wave function is symmetric. So we take a box as usual. We have non-interacting particles in the box. We quantized states in the box. So the energy epsilon P is P squared over 2m, and P is h bar k. And according to the theorem which connects spin statistics, we consider bosons with spin equal to 0. Okay, then we derived a Bose distribution function, and P, which was 1 divided by epsilon P minus mu over temperature minus 1. Once again, Kb is equal to 1. With h bar, I will tell you at which point I start with h bar equal to 1. For the moment, I keep it. So what we say that the distribution function, which characterizes the expectation value to find your particle in the state with a p, is definitely positive or non-negative number. Therefore, NPB for NP should be non-negative. Including state p equal to 0, which means 1 over e to the power minus mu over temperature minus 1 should be non-negative. Therefore, we say that mu is negative. Mu is non-positive. Otherwise, we cannot satisfy this property. And as I said, we anticipate that the chemical potential mu as a function of temperature should behave like that. This is our conjecture. And having said that, the chemical potential is negative everywhere temperature is larger than T naught and 0 below, we will find T naught. Namely, the total number of particles n is equal to sum over P and P bottom. So this is, we consider macroscopic system. Volume. There is no degeneracy associated with spin because we can consider bosons with spin equal to 0. So this is integral over dp over 2 pi h bar cube. And we said that this is e to the power epsilon p minus mu over temperature minus 1. So if we say, so the total density of the particles is fixed, therefore, if we want to find T naught such a way at this T naught mu is equal to 0, therefore, well, by the way, this equation, which I wrote, defines mu as function of n over v and temperature, because the concentration of particles is fixed. So if we want to find a solution for temperature in T naught at which chemical potential becomes 0, by the definition, we have n over v is equal to integral dp over 2 pi h bar cube 1 over epsilon to the p squared over 2m T naught minus 1. So this is the equation for T naught. Let's compute this integral coming to the energy variables. So we have dp as usual is 4 pi p squared dp. So this is 4 pi, since nothing depends on angles, dp times m dp squared over 2m. And this is 4 pi square root over 2m energy, d energy, m d energy. Therefore, this integral is 4 pi m square root over 2m divided by 8 pi cube h bar cube. And here we have integral from 0 to infinity square root of epsilon d epsilon divided by e to the epsilon over temperature minus 1. We make this integral dimensionless, introducing variable z, which is epsilon over t. Therefore, we have equation n over v is equal to m square root over 2m divided by 2 pi square h cube. So we have temperature to the power T naught. This is T naught because we are looking for T naught to the power 3/2 times integral from 0 to infinity square root of z dz e to the power z minus 1. So this is a number. Therefore, T naught is equal to, I will take this number, I know this is 3.31 h bar square over m n over v to the power 2/3. So therefore, we connected the temperature at which chemical potential becomes 0 with the total density. And if you recall the equation for the Fermi energy, this is the same power of the density to the power 2. The question is, what happens then? What happens at temperature below T naught? First of all, let's look at the same state T equal to 0, namely this one, when chemical potential goes to 0. So, since chemical potential approaches 0, and this is definitely much smaller compared to the temperature, we can write it down as 1 minus plus modulus mu over temperature minus 1. I expand and take into account that this is plus modulus mu. The chemical potential is negative. Therefore, the average number of particles with a state characterized by the wave vector equal to 0 is temperature over mu. So it diverges if mu goes to 0. The temperature is finite, chemical potential goes to 0. So basically what happens is that we have a macroscopic number of particles occupying the state characterized by p equal to 0. This phenomenon is called Bose-Einstein Condensation. The paradox which we might have if we do things in the wrong way is that if we adopt the same way of computation for temperature smaller than T naught, we get that the number of particles, the density over V, is proportional to the temperature to the power 3/2. And we reduce temperature, we get less and less particles. So what happens? And the wrong thing in this calculation at temperatures below T naught, that I should write down the terms with p equal to 0 separately. I have to write down that this is n naught over v plus the integral from dp to p h bar cube and p boson. So as I said, in the sum, I have to account on the macroscopic number of the particles occupying the state with the p equal to 0. And as a result, what we get is that n naught, the number of particles in the state with p equal to 0, is equal to total number of particles 1 minus t over T naught to the power 3/2. So this characterizes how many particles are there in a condensate. Once again, what condensate is? This is not like water droplets, the condensation in a real space. No, the Bose-Einstein condensation, and this is BC, occurs in the momentum space when there is a macroscopic number of particles occupying the state with p equal to 0. Let's assume that we have a wave package characterized by a certain wave length, the width. So this is a de Broglie wave. The de Broglie wavelength lambda is h bar divided by momentum. And if I'm talking about thermal wavelengths associated with temperature, we don't have interaction. So I'll write down that this is h bar over square root over 2m temperature. So we can consider bosons, which are non-charged particles on one hand, but waves, macroscopic states on the other hand. And if we see what happens if the de Broglie wavelength becomes of the order of the distance between particles, which is the concentration to the power 1/3. So then, let's put T star. Then we can write down that T star is precisely h squared over m and to the power 2/3. So the meaning of this T star, which is pretty the same as T naught, is the temperature when the de Broglie wavelength characterizing your wave package, characterizing to your wave state, becomes comparable with the mean distance between particles. If the temperature is smaller than T star, the de Broglie wavelength is larger. So you have a giant macroscopic coherent state, like a laser if you want, characterized by unique coherent wave function. So this is no more language of particles applicable to this case. If the temperature is larger, then T star, the Broglie wavelength is smaller compared to the distance, which means that we can speak about particles as separate objects. Once again, temperature is larger than T star. We have incoherent particles because their typical size, which is the Broglie wavelength, is smaller compared to the mean distance. If the temperature is below T naught, then we have a giant coherent macroscopic state characterized with unique de Broglie wavelength and characterized unique coherent wave function. So this is Bose-Einstein condensation. Any question about that? Okay, let me then proceed with thermodynamics. Let's compute energy. Energy is sum of p squared over 2m times n/p bar. So while computing energy, I don't need to care about the macroscopic number of particles in the state with the p equal to 0, because the energy of this macroscopic number of particles is 0. So therefore, in this sum, I am fine to replace it by integration. I don't need to separate the contribution coming from the state p equal to 0, because its macroscopic number is multiplied by 0. So what I have is volume integral p squared over 2m dp over 8 pi cube h bar cube times e to the power. At this moment, I will consider the energy of my bosonic system at temperatures below the temperature of Bose-Einstein condensation, T0. Therefore, if this condition is fulfilled, I am free to put chemical potential equal to 0. Once again, we are talking about non-interacting system, so this is E squared over 2mt minus 1. In order to compute this integral, I do the same as before, namely, I will replace my integration of a momentum by the integration of energy. So this is m square root over 2m divided by 8 pi cube h bar cube. And here I have integral from 0 to infinity, epsilon to the power 3/2 d epsilon e to the power epsilon over t minus 1. And once again, I introduce dimensional variables epsilon over t. So this integral is equal to gamma times volume, because this is extensive variable, in times temperature to the power 5/2. I'm not going to compute the constant gamma, it's just a number. I'm taking care about the temperature dependence, and temperature dependence arises from making this integral dimensions. Okay? Good. So, if I compute specific heat per unit volume, so all thermodynamic quantities are extensive, so this is the energy over the temperature at a constant volume. Plugging in the energy, I get that this is gamma, well, let me keep volume. Volume, temperature to the power 3/2, and I have 5/2 here. This is how the specific heat looks like. It's proportional to the temperature to the power 3/2. The thermodynamic relations tell me that the entropy, namely T ds over dt, is equal to specific heat. Therefore, the entropy S can be obtained as integral CVV as a function of temperature divided by temperature d temperature, and I have to apply the next law, which tells me that the entropy of my non-degenerate state at 0 temperature is 0, and I have to integrate it to the temperature. So this is how I get the entropy. So I plug in specific heat, and the entropy is gamma V times 5/2 integral from 0 to temperature. Temperature prime to the power 3/2 over temperature prime, d temperature prime. So I have temperature to the power 1/2. Therefore, this is gamma V times 5/2 times 2/3 times temperature to the power 3/2. So this is my entropy. Of course, it goes to 0 when temperature goes to 0. So this is 5/3 gamma V times temperature to the power 3/2. Okay? The free energy, F, which is energy minus T times S, which is then equal to gamma volume temperature to the power 5/2 minus 5/3 gamma volume temperature to the power 5/2. So this is minus 2/3 gamma V temperature to the power 5/2. The pressure P is minus d free energy over d volume so it is equal to 2/3 gamma T to the power 5/2. And if I multiply the right-hand side and the left-hand side by the volume, I will get my equation of state. So P times volume is equal to 2/3 gamma volume temperature to the power 5/2. This is 2/3 energy. Right? This is the same equation of state which I obtained for Fermi system. I didn't do any approximation, whatever. And once again, if I plug in the classical value of the energy, so the classical Boltzmann value energy is 3/2 n times temperature, I will get standard Clapeyron equation, which says that P dot V is equal to nt. Okay. However, let me also draw your attention to the interesting fact. The pressure which we compute doesn't depend on volume. If you remember when we computed the pressure for ideal Fermi system, it depends on the density to the power 5/2, so it depends on volume. This expression doesn't depend on volume. What does it mean? It means that only those particles which are characterized by non-zero energy, namely the particles which stay out of condensate, they contribute to the pressure, because they create some force. You can consider the walls of your containers. For those particles which are in the Bose-Einstein condensate state, they are characterized by zero energy, and therefore they don't contribute to the pressure. So basically, what you get is that this is the number. The pressure is then temperature times number of particles and time which is out of condensate. This is a physical meaning. Okay? Any questions? I hope you discussed Bose condensate at least a little bit in your course of advanced statistics. Did you? Actually, you didn't know. So this is the first time you read it? Well, in the last lecture about bosons, I showed you slides on the direction of Bose-Einstein condensation in cold gases of alkali metals. It became extremely hot topic in the recent, say, 10-15 years, because historically, I wrote everything on the blackboard. So the phenomenon of Bose-Einstein condensation was predicted by Indian physicists Bose and Albert Einstein in 1924. And since that time, people were looking for the implementation of this ideal state, and people didn't succeed. So for almost 70 years, experimentally, people didn't succeed to detect and observe this Bose-Einstein condensation state. Why? Well, the most natural subject, so let me write down that T naught is 3.31 h squared over m times density to the power 2/3, the most natural candidate for detection of positive condensation would be the lightest element in the nature, which is hydrogen. It's supposed to be characterized by the highest possible temperature of Bose-Einstein condensation. However, there is a problem with hydrogen. Namely, hydrogen, which is one proton and one electron, forms a molecule, H2. And this molecule, when you drop temperature below certain temperature, forms the ice, molecular ice. So this is not the Bose-Einstein condensation of the atomic hydrogen. In order to prevent hydrogen forming the diatomic molecule, one needs to apply magnetic field, which will then spin polarize the electronic term, and as a result, due to Pauli principle, you will not be able to form the hydrogen molecule. It appears that one first of all needs to have very high magnetic fields and then also very high pressure to get appreciable density. And as a result, the Bose-Einstein condensation over hydrogen was observed in late 19th, maybe, I don't know, several years after detection of the Bose-Einstein condensation in alkali metal because of the problems which I said. The second candidate for detection of Bose-Einstein condensation would be the next element, which is helium. And helium, which we will discuss in some details in the next and the lecture after the next, is indeed a subatomic system. However, it appears to be strongly interacting system. The fraction of particles in the condensate is less than 10%. So this is, of course, system where there is a possibility to have superfluidity. We will discuss superfluidity of helium. However, the superfluidity, as we will see, is attributed to the effects of interaction, and helium is strongly interacting system. Then people try to see it in semiconductor structures like excitons. The exciton is equivalent to hydrogen atoms in this bound state of electron and hole. However, in the semiconductor structures, the excitons are characterized by certain lifetime, and this lifetime appears to be quite short. So, indeed, it's a hot topic nowadays to detect Bose-Einstein condensation in the system of excitons or magnons. However, one really needs to take care about the lifetime of these quasi-particles. And with alkali metals, the first experiments were done with rhodium, which has a number 87, so it's quite heavy. And nevertheless, it was shown with experiments done by people working in quantum optics that the fraction of particles sitting in the condensate approach to 100%. This is 99.9. So this is indeed ideal system for detection of condensation, and it becomes a playground for playing with the physics of cooperative phenomena. It's of paramount importance for the methodology, and this is also an important part of the quantum computing business when people try to build a quantum computer. So this is why this topic, although being invented in 1924, becomes very, very important and rapidly growing field of modern condensed matter and quantum optics and atomic physics field of modern theoretical and experimental physics. Good. We are done with ideal gas. Let's turn on the interaction. So, really interacting. Let's quantify what does it mean to be really interactive. as I said, we consider bosons, which are neutral, non-charged particles. Therefore, the way they interact is when they approach to each other. Okay? So one can keep a cartoon of kind of balls which interact only when they collide. Therefore, if we characterize the quantum state with a certain size, let's say that this is typical d, which is the wavelength, if you like, or size of the wave function of the boson, we should say that the interactions are weak, provided that the size d is much smaller compared to r, which is the mean distance between particles. The mean distance between particles is inverse density to the power 1/3 for three-dimensional gas. Therefore, we write down that the density times d cubed is much smaller than 1. This is a gas parameter. This is a limit when we can consider the gas as weakly interacting system. So, without losing generality, I will assume that otherwise interaction between particle R1 minus R2 is delta function R1 minus R2. And as we'll see in next lecture, I will characterize the strength of the interaction G in terms of the scattering length, and this A, which is scattering length, I gave you a proper definition. Next time will be something which replaces D. Therefore, under this condition, I have n A cubed much smaller than 1. You see that the scattering length indeed characterize the strength of the interaction on one hand, but on the other hand, the scattering length for the quantum object is about of its geometric size. Good. So let me write down the Hamiltonian. Please pay attention that I consider the constant interaction, and at this moment I will put start with H bar. So the Hamiltonian is written down. I use the second quantized language. So this integral over d r prime, I open the brackets. So I have psi star r prime minus nabla over 2m psi r prime. So this operator, and the Hamiltonian is the operator. Right? This is the kinetic energy. Then I can assume that my particles are in the trap. So it means they are subject to some external potential r prime, psi dagger r prime, psi r prime. Okay? And then I should add that there is 1 over 2 factorial psi dagger I prime, psi dagger r prime, psi r prime, psi I prime. So this is my Hamiltonian, and since I plan to work in a grand canonical ensemble, I will subtract mu times n from the Hamiltonian. So this will be minus mu psi dagger r prime psi I prime. So this is the system I can consider. I can write down the Heisenberg equation of motion for the operator psi. You know that one can formulate the quantum mechanics using the equations for the wave function. This is the Schrödinger equation. Or, equivalently, one can formulate the quantum mechanics writing down the equation of motion for the operator. And these are Heisenberg equations. So I'm proceeding with the Heisenberg equations, which is minus I d over dt psi is equal to commutator h psi. So what I want to do, I want to derive equation of motion for the psi, computing the commutator. Okay? The left-hand side is quite clear. So what I need to do is to compute the right-hand side. So this is Heisenberg representation, and in this representation, operators depend on coordinated time. However, the important point that in this Hamiltonian, all interaction occur at the very same moment of time, so we neglect any retardation effect. Therefore, the Heisenberg operator taken at the very same moment of time can be characterized by sort of commutation relations, which help me to compute the commutation. Namely, I assume the two operators psi star, psi dagger, or two operators psi star just commute. The commutator of these operators is equal to 0. However, the commutator psi r prime minus psi r prime psi r is the delta function r minus r prime. So this is the commutator. So therefore, let me say that this is term number 1, this is term number 2, this is term number 3, and this is term number 4. I have some of these 4 terms, and I will commute them with operator psi one by one. So r, t, r. Let's compute the first commutator. Namely, I have integral over the r prime, and here I have psi dagger r prime minus nabla over to m psi r prime psi r minus psi r psi I prime dagger minus nabla over to m psi r prime. So this is the commutator of the first part of the Hamiltonian, namely kinetic energy with operator psi r. So these two operators compute. They are taken at the very same moment of time. I can write down that this is psi r prime. My nabla operator acts on the coordinate r prime, so I can take it out there. So in fact, what I have after the first permutation is psi dagger r prime psi r minus nabla over 2m psi r prime. So these two operators, psi r prime dagger psi r, I have to apply this commutation relation. Therefore, this guy is equal to psi r psi I prime dagger minus nabla over 2m psi r dagger prime minus delta function r minus r prime minus nabla over 2m psi I prime. So this term cancels out with this one. The integral with the delta function can be taken. So this is minus, then minus nabla over m times psi r. Okay? So with the second term, this is integral over dr prime psi dagger r prime v r prime psi r prime psi r minus psi r psi dagger r prime v r prime psi r prime. I will write it the same. This one can be commuted easily, and then I commute to others. So this is then minus v r times psi r. The term number 4, which has the same structure with the chemical potential, so this is then minus mu integral over d r prime psi r prime psi I prime psi r minus psi r psi r prime dagger psi r prime is equal to minus mu psi r, right? Then what I still need to do is to consider term number 3, which is integral over dr prime. And here I have g over 2 psi dagger r prime psi dagger r prime psi r prime psi r prime psi r minus psi r. I will put g over 2 out of the bracket, r prime psi I prime psi r prime psi. So the strategy, as before, is to commute this guy until it appears in front of all. Then something will cancel me the first term, and the rest is what I am out. Okay? So this one can be commuted, and this one can be commuted easily. So I end up with psi dagger r prime psi dagger r prime psi r prime psi r prime. So when I commute these two, I get permutable term minus delta function. Therefore, integral with the delta function will give me g half psi r modulus square psi r. And then I have psi dagger r prime psi r psi dagger r prime psi r prime psi r prime. Then I need to commute it again. So this is minus, by the way. And as a result, I have yet another term, g half psi modulus square r psi r. So I should multiply by factor of 2, and the remaining part will cancel out the last term in the brackets. Okay, so I have this term written twice. So let me now collect all what I So in the left hand side, I have minus I deep psi over dt is equal to minus I have minus nabla over 2m psi. Then I have plus dr psi rt rt. I have minus mu times psi rt, and I have plus g psi r modulus square psi r. So if you permit me multiply the right hand side and the left hand side by the factor minus 1, what I have then is I d psi over dt is equal to minus nabla over 2n plus vr minus mu plus dg psi r modulus square times psi r. Okay? So you see that what we get is a kind of non-linear equation. Sometimes this equation is referred as nonlinear Schrödinger equation or Gross-Pitayevsky equation. So where this nonlinearity, this one, comes from? We know that single particle quantum mechanics is linear because there is a principle of superposition. But here we have a quantum mechanics of many body interacting system. Therefore, we have a nonlinearity associated with interaction between particles. So the remaining part is just a simple quantum mechanics of a particle in external potential. The last term, nonlinear one, takes care about the interaction. So this is very important equation, which I'm going to deal with in the remaining half an hour of my lecture. Okay? Let's look at it. So, for the moment, although the experiments I'm going to refer to in my next lecture will be related to existence of the trap. Trap is described by confined potential originating from magneto-optical trap, the way people confine the gas. What I plan to do now, I will assume that there is no trap. I have a uniform situation. So, first of all, let's say the trap is 0. I come back to discussion of the trap. Even you'll have one of the problems in your homework, which will also relate to behavior of Bose-Einstein condensation in the parabolic trap. Then, I said that we discussing Bose-Einstein condensation. This is a peak, almost delta functional peak in the state characterized by the momentum equal to 0. If we take a Fourier transform of a delta function in a momentum state, in the coordinate state, you achieve the state, uniform state, when the wave function of your state is a constant. So this is what Fourier with the delta function gives you. Therefore, if we are talking about coordinate state, the macroscopic number of particles or operator psi in the uniform state can be replaced by square root over n, the density of particles. This is a uniform state. It doesn't depend on the coordinate and it doesn't depend on time. If I plug it in the equation, the right hand side, since this psi node doesn't depend on time, gives me 0. In that left hand side, doesn't depend on coordinate, is 0. Potential is 0. What I have is minus mu plus g times n times square root of n is equal to 0. So from this uniform solution, I actually find a connection between the chemical potential of interacting system and interaction. Namely, solving this equation, I find that the chemical potential is equal to interaction times density. So all particles are in the condensate. And it's not surprising that the chemical potential is not zero. You should not be confused with what I said before, because G is the interaction. The chemical potential in the interacting system is not zero. This is dE over dN. Therefore, you add some more particles in this system and you increase the energy. Good. Number two. Now, I would like to find the excitations in this system. Therefore, I would allow small oscillations of my wave function, macroscopic wave function, which is a number square root of n, which appears on the top of this uniform solution. So therefore, let me look for solution of my psi RT is square root of n plus some coefficient a exponent I k r minus I omega t plus another constant b star e to the power minus I k r plus I omega t. So I allow small oscillations of my wave function, and using this equation and linearizing it, I would like to find the connection between omega and k, which will give me the spectrum of my excitations. This is what I'm going to do. On Friday, we do differently. We will find the same spectrum in also quite lengthy calculations. Now, I would like to use this Gross-Pitayevsky equation, and I would like to find connection between omega and k. Allowing small oscillation, small means that this coefficient a and b are smaller compared by square root of n, and therefore I'm fine to linear.
This equation is the equation of motion, right?
Yeah. But as I said, I'm dealing with a classical macroscopic state. There is a macroscopic number of particles. Therefore, I can replace my operator by just some functions. Yeah, good. So, since I have long exponents, let me introduce you some shorthand notation. We are going to proceed with some calculations. So, I will denote this exponent as E plus, and this exponent as E minus. So, the left-hand side is I d psi over dt is equal to I. The derivative of square root of n is, of course, 0. Here I have A times minus A omega times E plus B times E omega, B star, E minus. So therefore, this is A omega E plus minus B star omega E minus. The strategy which I'm going to adopt, I will plug in, this is what I start to do, my wave function in the right-hand side and the left-hand side equations, and then I will collect all terms in front of the exponents, E plus and E minus, and as a result, since there are two linear independent exponents, I will get two equations, and I will solve these two linear algebraic equations. This is what I want to do. By solving these equations, I find some condition which will give me connection between omega and k. Good. So this is the left-hand side. In the right-hand side, I have term yeah. I have term mu times psi. So therefore, I have term minus mu. Let's start with kinetic energy. With kinetic energy, minus nabla over 2m applied to this gives me k square over 2m. And the same I can write down with minus mu. So I have k square over 2m minus mu a e plus k square over 2m minus mu b star e minus. This is the most simple term, and of course I have minus mu times square root of minus mu times square root of. Okay, so this is in the right hand side this term, and potential is 0. So now term with g plus g, I have to write square root of n plus e plus b star e minus times square root of n plus a star e minus plus b e plus. This is modulus square, and then once again square root of n plus e plus b star e minus. Let me look at this term. I will write down separately. So I have product of these two terms, and I have to keep the highest possible power. So I have g. Then n and n gives me power 3/2. Then I need to collect terms which will be linear in n. So I have square root. Let me then multiply it. So square root of n times square root of n, which give me n a e plus b star e minus. So this occurs when I multiply this n to this term. However, I also have this square root of n terms, which I then need to multiply by this. So I have square root of n multiplied now by something coming from cross term here. Cross term n. This is a plus b e plus a star plus b star e minus plus terms of the order of square root of n, which I'm going to drop. Okay? You follow what I do? I just open the bracket and do simple algebra. And I do linearization because I don't consider this wave square. So as a result, I have a omega e plus minus b star omega e minus is equal to k squared over 2m minus mu a plus a e plus k squared over 2m minus mu b star e minus mu square root of n plus g square root of n times n. This is this term, but you remember that mu is equal to gn. Therefore, these terms cancel out. from uniform solution. And then what I have is plus Gn A E plus plus B star E minus plus Gn A plus B E. I think this is E minus. Yeah, because I am multiplying what I'm doing, square root of n A plus B, no, A plus Gn A star plus B star E minus. Let me see whether I didn't do mistake. No, I didn't do. So now I need to collect separately terms with a plus. And with minus. Let's see again. A plus B, A plus B, A plus B plus. So, just see if I did not do mistake. Let me write it down. So, A omega. So I collect this omega minus k squared over 2m plus mu times A. This is the first term. Plus Gn A what I don't like is Gn A plus B. I have Gn A plus B. Just a second. Gn. Sorry. There is a term minus mu. Sorry. A E plus plus B star minus, and then this term no, I include it here. Let's do it separately. This term mu A plus plus B E minus. Mu A E plus minus B star E minus. And then there is a term Gn, mu equal to Gn. It comes with plus and minus. So I will cancel the term with A E plus, this one. And I cancel term this one. So now everything is okay. So there is no mu anymore in my equations because I eliminated it by Gn. Okay? You see what I did? So this term is precisely this term, and this term is precisely that term. And what remains is this. So I have omega minus k squared minus Gn A minus Gn B star, beam is equal to 0. This is the first equation. And the second equation is when I equate, this is exponent E plus. From the exponent E minus, equating these two terms, I have minus omega b star is equal to k squared over 2m b star plus gn a star plus b star, coming out from that term. Okay? Plus omega a is equal to k squared over 2m a plus gn a plus b. So this is the first equation, k squared, and gn a plus b. And this is the second equation. So I will take a complex conjugated from the second equation. So therefore, I will eliminate star everywhere. Good. So I have a system of two linear equations. And the system has a solution. It's a uniform equation when the determinant is equal to 0. So omega minus k squared over 2m minus gn a minus gn b is equal to 0. Gn a plus omega plus k squared over 2m plus gn b is equal to 0. So the spectrum can be obtained by equating the determinant, which is omega minus k squared over 2m plus gn times omega plus k squared over 2m plus gn plus gn square is equal to 0. So therefore, omega squared is equal to k squared over 2m plus gn square minus gn square. Or it is equal to k squared over 2m plus 2gn multiplied by k squared over 2. Good. So, what did I obtain? I obtained that omega k is equal to square root over gn times k squared over m plus k squared over m squared. This is a remarkable spectrum, which first of all possesses the following property. First of all, you see that my excitations are gapless. I don't have gap. Second, if we plot this dispersion, omega k, which depends on k, for small k, it depends on k linearly. Namely, we have omega equal to ck. It's a sound. It's a propagation of phonons. So the excitations in interacting, really interacting, with a gas are phonon-like. This is a sound. So you see, I did not have any lattice or whatever, and the phonons do not need any lattice. When we speak in the room, we also propagate phonons because phonons are associated with the density fluctuations. For large A, however, it behaves as k squared over 2, as free non-interacting particles. So this spectrum is known as Bogoliubov spectrum. And the existence of gapless branch of excitations is sometimes referred to as existence of a Goldstone group. You probably discuss it with Professor Nersian. So the existence of gapless excitations of Goldstone mode is associated with breaking of certain symmetry, right? What kind of symmetry is broken here? With condensate, we break U1 symmetry. Actually, your Hamiltonian you began with provided symmetry with respect to the phase, the gauge transformation. But when you introduce a condensate, namely you assume that there is a macroscopic number of particles which is accumulated in a state characterized by the wave vector equal to 0, you break this symmetry. We will see on Friday precisely how it happens on the level of Hamiltonian. We will start with the very same Hamiltonian and diagonalize it using wave vector transformation, the very same way as you did it with Professor Nersian for magnons. And we will see that, in fact, we break some symmetry by Bose-Einstein condensation, and as a result of a combination of interaction and broken symmetry, we arrive to the Goldstone magnon. But let me make another remark, which is discussion of non-interacting and interacting gas. So for non-interacting BG, when we discuss Bose-Einstein condensation, we said that epsilon p is just p squared over 2m. The free particles. In a sense, this is lambda times e squared, and this is equivalent to the spectrum of ferromagnetic magnons in ferromagnets. So, in a sense, the non-interacting Bose gas is of the universality class of a ferromagnet, while the interacting, weakly interacting Bose gas, we found that epsilon BP is Cp in a long wave limit. This is a dispersion of excitations. Therefore, the weakly interacting Bose gas is of the universality class of antiferromagnets. Then, there is a still phase transition, I said, and I actually computed the density, and if one considers the density of particles in the condensate as an autoparameter, then we see that there is some non-zero density of particles in the condensate below T node. This is indeed the phase transition. Did you have discussion of phase transition in any course? Do you know the classification of the phase transition, so-called Landau and test, which says that the thermodynamic potential, like energy or free energy, is always continuous. The entropy is the first derivative. The specific heat is the second derivative. So in the second order phase transition, your specific heat has a jump. So it has a continuity, while the entropy has a kink. So it's continuous, but the derivative at the phase transition point from the left and from the right don't coincide. This is the second order phase transition. Second derivative has discontinuity. The first one has kink. If we speaking about first order phase transition, what is typical first order phase transition? You boil your water in a teapot. You bring some heat into the system, but temperature doesn't change. Therefore, the specific heat at the phase transition point of boiling just diverges. The entropy has jumped. The energy is, of course, continuous. Therefore, the first derivative of thermodynamic potential has discontinuity. Therefore, one can characterize the order of phase transition by the order of the derivative of the thermodynamic potential when the first discontinuity appears. So, in the first order phase transition, first derivative becomes discontinued. In the second order phase transition, the second derivative becomes discontinued. So, my question to you, if we consider ideal Bose gas, I explained you thermodynamics. We computed specific heat, and we saw that specific heat is continuous. So the question is, try to think about the phase transition into B state as a phase transition, and determine the order of phase transition. Which derivative will have discontinuity? This is my question to you to think about. And another thing, interestingly, we found that the phase transition appears in non-interacting system, in non-interacting bosonic system. So the system collapses into this BC state, and for curiosity, we restrict the question if we have kind of phase transition in ideal bosonic system, if there is a phase transition in ideal fermionic system without interaction. And the question is yes, there is such kind of phase transition, which is associated with the change of the topology of the Fermi surface. In ideal gas, you have Fermi surface, or better say cyclotronic orbit, which is closed or not closed. And just to give you a hint and computation, the phase transition according to Landau-Ehrenfest classification to BC going to be third order phase transition. Do computation show it that the derivative of specific heat will get a jump. And this is why sometimes this phase transition in ideal system is called lambda point. So specific heat has king and resembles lambda. But in the harmonic system, we probably come to this discussion at the end of the course. This is so-called 2.5 order phase transition, because there is a certain power. When we discuss Ginzburg-Landau and Landau theories, we will see that the coefficient, when we approach to the phase transition point, behaves as a certain power of the distance from the point. So determining this power will also give you the order of phase transition. And the last comment, which I would like to make, of course, we did these calculations assuming that the interaction u r minus r prime is g delta function r minus r prime. So I start with contact interaction. On Friday, I will do a general derivation with Bogoliubov transformation, but let's just turn on the fantasy and assume what happens if your interact, if a few bosons are charged, could happen, and what happens if bosons interact through Coulomb interaction, if you have a charge. So in this situation, we need to replace G by 4 pi e squared over k squared, right? And if we plug it into the dispersion, what we will get that the spectrum, Bogoliubov spectrum of charged bosons is gapped. So omega is equal to square root over 4 pi e squared n over m, because k squared cancels out, plus k squared over 2m squared. But what you see here is precisely plasmon frequency, which we discussed last time. So omega plasmon square is equal to 4 pi e squared and density divided by mass. So in the case of Coulomb interaction, your Goldstone mode disappears, so to say. And this is another important observation. We will see how it happens in superconductors. So in a charged system with a long-range interaction, you don't have a Goldstone mode in a sense, because Goldstone theorem addresses the situation with a short-range interaction to the system. And in superconductors, we will see that there is a gap associated with the fact that the superconductors is formed by Cooper pairs, which are electrons forming kind of, I would not call it bound state, but some coherent state, which then results in global instability of your ground state with respect to formation of the Cooper pairs, which is again first order phase distribution. Okay, that's all for today. Any questions? Please.
Is it possible to have one authentic condensation of phonons?
Well, phonons are particles with zero chemical potential. You see that in order to, this is the chemical potential. You cannot condense phonons. You cannot condense photons because these are particles with zero chemical potential.
The report that before is looking for authentic condensation of magnons.
That's true, but for magnons, you know, there is acoustic magnons and optical magnons. The optical magnons are characterized by the gap, which plays a role of the chemical potential, in a sense. There is energy gap. The same for polaritons. If you trap your photons and then organize a bound state of photons with excitons, in optical cavity you can trap photons in one direction. It will acquire some mass. Mass is equivalent to the gap. Therefore, by engineering the optical cavity and special geometry of trapping, you can also discuss the Bose-Einstein condensation of polaritons. Not photons, but polaritons.
Just to extend on this question, does this mean that there will only both Bose-Einstein condensation if the chemical potential at finite temperature is not zero, but then as it approaches the critical point it becomes zero? But
well, we should not confuse chemical potential of non-interacting system and chemical potential of interacting system. So therefore, Bose-Einstein condensation appears in ideal system as well. But the superfluidity, which is a benchmark of coherent properties of bosons, is actually very closely related to phenomena of Bose-Einstein condensation. One needs to get Bose-Einstein condensation to have a superfluid state, but one needs to get more. One needs to have interaction, because only with interaction one gets, first of all, non-zero chemical potential and sound velocity, which is proportional to the square root of interaction. And then, as we discussed on Friday, the system with a sound-like light spectrum can be superfluid. Therefore, it can flow through the capillaries without any friction, because there is a criterion, so-called Landau criterion, I will tell you Friday, which teaches you what is a critical velocity of your flow, below which it doesn't emit phonons into the walls. Therefore, it can proceed flowing through capillaries without friction. And the same as with superconductors. You can have a current which flows through your wire without any resistance, without energy loss, but there is a critical current. You cannot make arbitrary strong high current. There is a critical velocity and critical value of current, after which the superfluid state is destroyed.
This another question. We wrote the interaction in the Hamiltonian a while ago by the gradation operators all in front. This means that there's no self-interaction, right?
Say it again?
I mean, the interaction term is like G, then side dagger, side dagger, side.
Yes.
All of the creation or the field operators with the daggers in front. This prevents any self-interaction, right?
Well, this is just normal ordering. You put the creation operators first, and that's it. You can always write down your Hamiltonian in such a way. This is the way you write Hamiltonian. Well, self-interaction is something different, but in a sense, right. Normal ordering is written in order to get rid of any discontinuity associated with self-interaction. Anything else? Any questions? I forgot to say that typically I take 1-2% for many research project at the end of the course. I would not be able to take 3 persons. Therefore, because it's too much, typically my field of expertise is quantum transfer strongly correlated systems, including Bose-Einstein condensates. So if you are interested in doing mini research project, you need to approach me sometimes before exam, because I would like to talk to you and before taking my decision whether we can, whether I can offer you some research project or not. And as I said, it includes Bose gases, superconductivity, magnetism, and mostly it's analytical work. I'm not involved in numerical simulations. However, sometimes in order to solve the equations which you get, you need to use some numericals. Good.